Welcome to the flipped content for the UCAS Visit Day at Swansea University Department of Chemistry. I'm Andrew McKinley, I'm a physical chemist in the department, and I want to give you a brief overview of spectroscopy, which we will then further discuss when you come to visit us. So the first question, of course, is what is spectroscopy? Spectroscopy quite literally is looking with light. It's the interaction of radiation and matter, and looking using a spectrometer, a sketch overview of which is shown here, using a spectrometer to analyse the content of our sample and what characteristics it might have. When we think of spectroscopy, we think of a spectrum, and the spectrum we're interested in is the electromagnetic spectrum. So this is the electromagnetic spectrum, and it's classifying the different colours, as we might think of them, to characterise matter in the way it interacts with that energy. Of course, the visible spectrum is only a very tiny proportion of this in the middle, and there's a huge amount that we just cannot see. But this is where spectroscopy comes in. We build instruments to allow us to see these transitions. In order to understand what's going on with spectroscopy, we need to know a little bit of basic quantum theory. Quantum theory is all to do with energy, and it's to do with energy transitions. Now, classical theory, classical physics, says that energies can be any value at all. But quantum theory, on the other hand, restricts us to particular steps. So it says the molecule can only have certain values of energy, and it can only transition between these specific values. To put it another way, if we imagine our molecules in the classical environment, these molecules can freely transition and move between any energy level we wish. However, quantum theory says that these molecules have to be on particular steps. So whenever they absorb energy, they have to absorb exactly the right amount of energy to jump them up to a particular step. And they wink out of existence on one step and appear on a higher step. And this is the central idea of quantum theory. To put it in a slightly more tangible way, if we think of a ladder, when we're climbing a ladder, we can only occupy the space on the rungs. We can only occupy specific sites on that ladder. Sadly, as much as we might want to, we can't fly. We have to occupy specific sites. So a quantum is that smallest possible indivisible unit of a quantity or quantifiable phenomenon. In this context, we're thinking of a quantum of energy. Spectroscopy fundamentally is the study of transitions. It's the study of what happens within a molecule when it goes from one energy state, in this case E1, to E2. The energy gap we think of as this quantity called delta E. This is just a change in energy. And when that molecule, here represented by the blue sphere, absorbs a packet of energy, it jumps up to the higher energy level. And we see that as a gap in the spectrum. Here this absorption is given by plus h nu. Nu is the frequency of the incident radiation. Of course, the reverse is true. If we have a molecule in an excited state, it's in the E2 level, it can shed some of its energy. It can get rid of some of that energy as a photon. It shines this out as radiation and drops down to the lower energy. Again, that frequency of that emitted radiation is a signature, fingerprint of the energy gap between the two energy levels. These energies, this h nu, is a fundamental term in physics. It's the Planck relation, where it relates the frequency, nu, to the energy of the photon using Planck's constant h. Using hc over lambda, we can determine the energy of that instant photon. So this is our visible spectrum. It goes from 700 nanometers in the red down to 400 nanometers in the blue-violet. So this visible spectrum concerns the motion of electrons. So it looks at how electrons move between atoms and molecules. That's the energy band that we're looking at in the visible spectrum. This leads us to a tool called ultraviolet visible spectroscopy. Very, very simply, we take our sample and we shine a beam of light through it, and we look at how the intensity of the light varies as it passes through the sample. So we take the instant radiation, I0, and we relate it to the transmitted radiation, I. And this frequently uses the Beer-Lambert law to determine concentrations of samples, which tells us that the absorbance A is proportional to the concentration of the sample, C, multiplied by the path length through the sample, and this has a proportionality constant called epsilon, which is the molar extinction coefficient. This gives us information about the concentration of the sample. So let's have a look at a very simple molecule, butadiene. So butadiene, very simple molecule. It has 4 carbons, 6 hydrogens, and 2 carbon-carbon double bonds inside that molecule. Now these double bonds are what we call pi bonds. And if we look at this, this means that each pi bond has 2 electrons. So overall in this molecule, there are 4 pi electrons. There are 2 from the first pi orbital on the right, and 2 from the second pi orbital on the left. When we study the UV-Vis spectroscopy of this, we find that it has a very strong absorption at around about 215 nanometers. Now, if we remember the Planck relation that we spoke about earlier, we just want to get a handle for how much energy is in a photon of light, in this little packet of light at 215 nanometers, which is absorbed. So what we're going to do is we're just going to do a quick calculation. So when we think of our photons, we want to try and think about what energy they have going into the molecule. So we've been told that the wavelength maximum, lambda max, is at 215 nanometers. Now we need to quantify a few things first before we carry on. We need to know the value of H. So the value of H is 6.626 times 10 to the power minus 34 joule seconds. So the units are really, really important here. But you can see Planck's constant is very small indeed. It's one of the smallest values that we use in science. The next one we need is this C parameter. So C is the speed of light. And that again is a constant, which is defined as 2.998 times 10 to the power 8 meters per second. Okay, so we have all the information we need to determine the energy of our photon, which is, as is shown there, we have H times C over the wavelength lambda. And this will give us the energy in joules, or it should. This is what we're expecting. We'll just check it with the units as we go through. So we need to put the values into our equation. So this is equal to 6.626 times 10 to the power minus 34 times 2.998 times 10 to the power 8. Now we mustn't forget the units, times joule seconds times meters per second. We then divide this by our wavelength, 215 times 10 to the minus 9 meters. So this times 10 to the minus 9 meters is the same as a nanometer. Okay, now we could put these values into our calculator. But firstly, we don't always have our calculator with us, and secondly, we don't need to have the exact value to understand what's going on. So let's do some approximation. Let's simplify this equation a little bit. So we'll just do it approximately. What we're going to do is we're going to take the significants out, combine them, then we're going to take the exponents out, combine them, and then we're going to take the units out and combine them. So firstly, we have 6.6 times 3-ish divided by 215. We then combine our exponents, times 10 to the minus 34 times 10 to the 8 divided by 10 to the minus 9, and then we combine the units, times joule seconds times meters, meters per second, divided by meters. Okay, so now we've got something that we can quite easily start approximating. We know that 6 times 3 is 18, 7 times 3 is 21, so 6.6 times 3 is going to be somewhere between those, so we're going to estimate that's going to be around 20. And then we divide that by 215. Now we need to combine our exponents. We do this by adding them together. This negative brings the 9 up to the top, so we have 10 to minus 34 times 10 to the power 8 times 10 to the power 9, and all we need to do is add all these up. With the units, these combine relatively simply. Seconds per second, they cancel. Meters and meters cancel, leaving us with joules, which is exactly what we were hoping for. Simplify this one more time. 20 divided by 215 is approximately 0.1. It's going to be a little bit less, of course, but we're just after understanding what's going on. Which is 0.1 times minus 34 plus 8 plus 9 gives us 10 to the power of minus 17 joules, which, representing in correct standard form, is 1 times 10 to the power of minus 18 joules. Now this doesn't look like a huge amount of energy, but this gives us the energy per molecule. In order to compare this and understand it in the context of other energy quantities we're familiar with, we want to combine this, and we want to, rather than have an energy per mole, we want an energy per molecule. So let's do another quick calculation. So we've already said that the energy that we have is difference in energy is 1.0 times 10 to the negative 18 joules per molecule. So every molecule will absorb this amount of energy. Now if we have 1 mole of molecules, that means we have Avogadro's number, Na, of molecules, and we remember that Avogadro's number is 6.022 times 10 to the power 23. So if we multiply, and we mustn't forget the units, which is per mole. Now we multiply Avogadro's number by this energy to find out the molar energy, which will come out as 1.0 times 10 to the negative 18 multiplied by 6.022 times 10 to the power 23 joules per mole. Again, combine the significance, we get 6.0-ish. We combine the powers, which is negative 18 added on to 23, which gives us 10 to the power 5 joules per mole. Or to put it another way, this is 600 kilojoules per mole. Now hopefully this allows you to see it in the context of a bond enthalpy. So if we think about hydrogen, the hydrogen molecule bond enthalpy is around about 400 kilojoules per mole. So you can see that this ultraviolet radiation, this 215 nanometers, which carries 600 kilojoules per mole, would be more than enough to break a hydrogen-hydrogen molecular bond. So what is actually going on inside butadiene to make this happen? So inside the molecule we have these two pi orbitals that we're thinking about. We're going to ignore all the others because not a lot is happening with them with the UV transition. Now, each orbital, each pi orbital, is at a slightly different energy. We'll come on to that when in first year chemistry. At a very slightly different energy, but you apply the principles you're already aware of. We have 4 of these pi electrons, and remember your Aufbau principle, we build up these bonding orbitals from the bottom up. And these electrons in this top pi orbital we call the highest occupied molecular orbital. So this is our highest occupied molecular orbital, and the electrons are actually coming from this orbital. Of course, where are they going? It turns out that we have 2 other orbitals to consider as well, and these are what we call antibonding orbitals, and we call these pi star orbitals. And the lowest of these, pi star 1, is called the lowest unoccupied molecular orbital, or LUMO. And what we're looking at is this HOMO to LUMO transition. We're looking at the delta E, the difference in energy between the HOMO and the LUMO. And that's what we've calculated. For butadiene, the electron absorbs a photon of radiation and is excited to the LUMO. And that energy gap, as we've just calculated, is 600 kilojoules per mole. Another form of spectroscopy is infrared spectroscopy. This probes molecular vibrations and rotations, allowing us to look at the nature of chemical bonds, in particular identifying functional groups within molecules. If we look at a molecule of carbon dioxide, infrared radiation, the correct energy of infrared radiation, will be absorbed by the carbon dioxide and will make it vibrate. And this is what's happening at a much lower energy than the electronic transitions. So when you're doing infrared spectroscopy, thinking about propanone, you will be looking at its spectrum, and the key stretch you're looking at is this peak at around about 1700 wave numbers. This energy is a signature of the carbonyl stretch, the C double bond O stretch, and this gives us a fingerprint of the molecule, but looking at the way in which it vibrates. The last part that we're going to look at quickly is nuclear magnetic resonance spectroscopy, or NMR. So this uses radio waves to flip the nuclei upside down. That's one way of thinking about it, and it tells us a little bit about the hydrogen environment. So what do we mean about that? Well, it's actually probing magnetic fields. So when we think of our proton, or think of our nucleus, some nuclei are magnetic. It turns out that protons, hydrogen nuclei, are magnetic. So instead of thinking of it as a sphere, let's think of it as a small bar magnet with a north and south pole. And what we do is we apply a much stronger magnetic field around it. We put it in a huge magnet, which makes all of these nuclei align to the magnetic field. Now this is what we call a stable equilibrium. But if we put in exactly the right amount of energy, this can make the magnet flip upside down. Now it's very unstable in that situation, but it is exactly upside down. But any small disturbance will make it revert back to its original alignment, and it will give out another photon of radiation. And this allows us to probe the strength of the magnetic field around a particular nucleus. You can think of this as a Weeble. So our magnet, if we think it has 2 energy states, the base energy state, the lower of the 2 energy states, is where our Weeble is really quite happy, and it will quite happily rock back and forward, but it will stay in that low energy state. But if we put in the exact amount of energy, we can make the Weeble balance on its head. It's very unstable, but it will sit there. However, it will readily relax back down to its ground state very, very rapidly. In our class session, we're going to focus on UV spectroscopy. You're going to be sketching spectra based on the observations that we're going to give you, and we're going to discuss a little bit about probability of photons causing transitions. And finally, we're going to show you a little bit of the advanced applications of the techniques. I've been Andrew McKinley, and I look forward to meeting you at your visit day.